Greetings everyone. In the last installment of this new series, I showed you the offset dish, the Bell Express View offset dish that I will be using for my permanent tower installed 10 GHz narrowband communication system. Now in this video, we will look at what's next, and it's the feed point itself for 10 GHz, 10368. And we have a few options on the table here. Some are good, some are bad. I'd like to briefly discuss the options. The obvious one would be to recover the feed point that was already on the dish for many reasons. Well, first of all, the frequency of operation of the previous system for DSS, like digital television, is between 10.7 and 12, 13 gig. So depending on the band, it's actually in Canada here, it's more like 11.5, I think, to 12.7 or something like this. So it's a little higher in frequency. And if you look at some existing systems that I had here, and this one is exactly the one I recovered from the dish, and it's a dual port feed point. The horn is what you see here. Okay, I've recovered it. We'll talk about it later. And this waveguide, the tube here, was obviously right here with the horn at the other end. I cut it off to experiment a bit with it. So this has some very valuable electronics. And it's the same for this guy here. This guy's designed 11.7 to 12.2 gigahertz, okay? And yeah, it has the same type of horn and PCB inside, which is chock full of RF components, and one important feature being a very good low noise preamplifier. If you want to use this as a LNA, you can by recovering the PCB like I did in my portable 10 gig system series. I used a PCB like this one, and so it's valuable. Unfortunately, the horn itself and the waveguide inside will not work for our application. Here is why. The diameter of the waveguide inside these guys, and take the dish network feed here, is 16.5 millimeters. And 16.5 millimeters is too small of a diameter to sustain and carry a wave of 10.368 gigahertz, unfortunately. Circular waveguides like this pipe here, they have a range of frequencies for which they're going to work to propagate with very low attenuation, and that range for circular waveguide sits between 0.61 and 0.77 times the wavelength. So 0.61 lambda, so 0.61 times the wavelength, is the smallest diameter that a circular waveguide will work. And that corresponds to 17.6 millimeters for 10.368 gigahertz. And what I have here is a 16.5, so too small, unfortunately. So same for this guy here, too small to sustain a 10 gigahertz, 10.3 wave. And the mode of propagation, just to let you know, this is something we learned at university in the microwave theory, microwave propagation, antennas and everything. It's a very arid book to read, trust me. We learned exactly about this, that the lowest cutoff frequency can be achieved with the transverse electric, the TE11 propagation mode. There are different modes that can propagate inside a waveguide, and the mode that is favored here is the TE11 that allows the lowest frequency to carry inside, and it requires a minimum of 17.6 millimeters. So unless I had access to a milling machine or very large drill bits, for me it's not possible to use this. I could certainly mill out some material if I had a milling machine, like a lathe, actually would even be best. There's enough wall thickness to machine something to reach the 17.6. Unfortunately, I'm not equipped to do this. So what did I do? To try to recover maybe a bit of it, I cut off the waveguide and I used another aluminum tubing that I had, similar to a cigar tube, cigar case, whatever, I don't know exactly how it's called in English, but cigar tube, I'd say. Only a little thicker though. It's not really a cigar tube. Cigar tube would be the proper diameter, but it's very, very thin. This one is a little thicker, still very thin though. You cannot thread anything in that tube. But this one has 19.2 millimeters, which is within the range of diameters to properly sustain a TE11 propagation inside. So what I did is I recovered the horn itself, the part with the steps here. I said, well, let's try. I kind of understood that the wall height is sufficient to work at 10.368, so I said, why not give it a try and fit it over the pipe here. And what I had to do is cut it off and file off a little bit of diameter, and really not much, and the whole thing fit inside. And I tried it, just to give you a hint. I tried it, I installed a probe and I adjusted the probe length, and I used some recipe from W1 GHz on where to put the probe exactly. There's a small probe inside, I can show you. Yeah, we can see it. Okay, so I did try to tweak the probe length to get to 10.368, and I slid the horn inside and out, and notice that the best position for best standing wave was not down flush with the lowest part. It was when I push this thing backwards and the tube comes up to the same height as the first ring. And I got 10, 11 dB of return loss, maybe 12, I'm not sure. So it sort of worked. Not superb. Maybe if I spent more time optimizing it, I could get something a little better. I did make a back wall that I could slide over it to extend and move in and out the back wall to see how much it would affect. And where I had cut it is pretty much where it should be for best VSWR. And I did also manufacture a wall I could slide in and out by pulling on the tab. And one thing to mention also is these horns are normally designed for circular polarization coming in, and there are features inside to convert or separate the vertical and horizontal polarizations, and this is called a septum wall. It's a piece of dielectric with a specific shape and installed in the right location. And of course, because we work in linear polarization, we don't need this, so I tore it out. I just cracked it and pulled it out, okay, to reveal the full waveguide. But still, that didn't fix my problem of minimum diameter, of course. Just to let you know, normally these horns are designed for circular polarization, but we can make them work in linear polarization. In our case, it's horizontal polarization, just by removing that feature inside. This one is a little different. As far as circular polarization, there are two probes inside, positioned right angle one with the other, of course, and they're not right next to each other. One is more forward than the other for phasing reasons. And there's another rod, there's a stainless steel rod inside that goes right across somewhere between the two probes. My understanding is both polarization work on the same frequency from the satellite, so you definitely have to separate horizontal and vertical, and with enough isolation to be able to pick up one or the other signal, because it's two different TV programming depending on the polarization you choose. Okay, so that's about these horns. Again, many things are recoverable. Maybe I would have gotten somewhere with this if I pushed more. I can tell you, I compared to this, and we'll talk about it in the next video, this horn, but it was not matching in terms of performance. It had at least 1 dB less performance than this guy. But like I said, Maybe I didn't spend long enough time, but there's another big challenge with these. It's made of aluminum. And when you talk about aluminum, you talk about dissimilar metal with copper or brass, and you do not want that. It's a no-no. As soon as there's moisture, there's going to be some corrosion, so metal migration and white powder and everything, you're going to get a bad contact. So when you work with aluminum, you have to find a way to transition to copper, not directly copper onto aluminum. And this is one big caveat using aluminum. If I found a copper tubing, it would be much better. Could I fit this horn, the pavilion on it, the horn? Maybe if I put something in between, some sort of film to make sure that there's no direct contact, it would still work. Even though there's no electrical contact, it would probably still work. But like I said, you cannot have copper and aluminum, which this is made of aluminum, direct contact. It's a recipe for disaster in the short term. Trust me, I've tried it. It does not work well. Okay, so this is for this horn. Now there's other possibilities. This is a off-the-shelf horn that was made for the military in the US. It's called an AT-68/UP, and it's quite readily available if you look on eBay and other places. This one's not designed for 10 gig. It's actually designed to stop at around 9.6 gig, but it can easily be tuned, and this one clearly was. I read 1.2 to 1 the VSWR at 10.368 with this horn. And it's by default though designed for 8.5 to 9.6 gigahertz. Okay, but it can be retuned with a small screw or magnet or whatever. There are ways. Unfortunately, this horn is not suitable for my dish because the pavilion, the horn is too narrow. It doesn't flare wide enough to fully illuminate my dish. So this, and I measured the difference of a couple of dBs, this versus this guy here. Okay, so yeah, we're left with this guy. This is a rectangular horn, and it will be the subject of my next video, but suffice to say, I made it myself following a recipe, and it works super well, okay, compared to the other feeds. So far, that's the best I can get, and it will be the subject of my next video. And by the way, if you use a piece of semi-rigid coaxial cable like this and you expose a probe with around 1/4 wavelength long at the end, you cut the copper shield and the Teflon dielectric, and you just expose a probe, you'll get 2 to 1 or even better VSWR out of this thing. And so it's possible to use just this little probe as an antenna for testing purpose if you wish to. It's possible. If you wanted to improve performance, you could add a small disc here, a copper disc maybe, that would slide over the exterior of the UT141. This one is UT85, I believe. It's a smaller semi-rigid, but you could use the bigger one, the UT141, and just install a small disc and create a ground plane antenna with just this. So it works. It's possible. If you need a quick antenna for like I said, a source, it's possible to use something as simple as that. Okay, so bottom line is, this is the avenue I'll be choosing, and I will detail this in my next video. You'll see it's pretty interesting. And then we'll do some measurements of this thing on the real dish in the following video. Until then, 7-3.